Trigonometry, Chapter 3, Radian Measure in the Unit Circle. Section 2, Applications of Radian Measure. Video 3, Simultaneously Rotating Gears. This series is based on content from Pearson's Trigonometry 12th edition by Lial, Hornsby, Schneider, and Daniels. In the previous video, we learned how to use the arc length formula to find the distance between two cities that were on the same longitude line. In this video, we will learn about the relationship between two rotating gears. When two gears of different radii are connected, either by teeth, as illustrated here, or by a chain like on a bicycle, the angular velocity, how fast it's rotating, is different between the two, assuming the gears are different size, which I implied here. As a consequence, the velocity of the larger gear would cause the smaller gear to rotate at a faster velocity. But why? Think about the arc length traveled by a certain point on the larger gear. So we'll take the intersection point and then it moves along this larger gear. The same point would have to travel just as far around the smaller gear in the same time. So in this picture, the green arc and red arc have the same length. Since both points travel the same distance in the same time, but the green one covers more of the circumference, the smaller gear has to rotate faster than the larger gear. Thus, a larger gear, such as pedals on a bicycle, can generate a faster angular velocity for a smaller gear, such as the gear on the rear tire of a bicycle. But for now, let's just analyze the relationship between the angle of rotation for both gears and not necessarily the angular velocity. We could adapt easily. Let's suppose the first gear has a radius of R1. I know it says 2.5, but we're being generic. And the first gear rotates an angle of theta 1, and the second gear of radius R2 rotates an angle of theta 2. The arc length traveled by a point on each gear is given by S1 equals R1 theta 1 and S2 equals R2 theta 2. But we already said the arc lengths were equal, which means we can take the R1 theta 1, the R2 theta 2, and put them equal to each other. And when we do, we get something like this. R1 theta 1 equals R2 theta 2. This is our equation relating the radii and the angle of rotation of two gears. Now, before we use this equation, let's discuss the unit of measure for the angles. The arc length formula does require theta to be in radians, but what if they were given in degrees? Well, we know what we would do. We would convert them both. If the angles were given in degrees, we'd multiply each by pi over 180 to convert it to radians. And if we did that inside of the equation, it would look like this. Both angles converted to radians by multiplying by pi over 180 on both sides. On both sides, well, afterwards, we could multiply both sides of the equation by 180 over pi. That would cancel the pi over 180s on both sides and change the equation to this, which is the exact same equation before we converted degrees to degrees and radians. Before we converted degrees to radians. This simply means that the equation works regardless of how the angles are measured. So unlike arc length, if we're comparing angles of rotation for gears with this equation, we don't have to convert to radians. For example, and here's the example for the picture. Suppose two gears of radii 2.5 centimeters and 4.8 centimeters are interlocked with teeth. If the smaller gear rotates 225, how many degrees will the larger gear rotate? Round to the nearest degree. Well, we have a convenient equation. The product of r and theta is equal for each gear. We have R1 equals 2.5 centimeters, theta 1 equals 225 degrees, and R2 equals 4.8 centimeters. So we substitute into our equation, and we get 2.5 centimeters times 225 degrees equals 4.8 centimeters times theta 2. Instead of multiplying on the left, let's go ahead and just solve for theta 2 by dividing by 4.8 and get this, and then put all of that into a calculator. The centimeters will cancel, by the way, leaving degrees. If we enter this into a calculator, we get approximately 117 degrees. So pretty straightforward. Small little equation for relating the rotation, the angle of rotation and the radii of two interlocking gears. Now you try. Pause the video and try the following. Find the radius of a larger gear if the smaller gear of radius 11 centimeters rotates 80.0 degrees when the larger gear rotates 50.0 degrees. Pause the video, give it a try. All right, here's your fair warning if you haven't paused the video yet. Solution in 3, 2, and 1. Notice I didn't actually use a calculator until the very end. That's good practice.